Friends, we are continuing with our next series of videos on data science, and today's video is going to be on temperature control lab, learn proportional integral derivative PID using machine learning. This is the part 3 of the video. You should always watch the earlier 2 videos to get continuation of PID using machine learning. As you can see on the screen, today's topic is going to give you an idea about the plot which is on the screen, where you can see that the temperature in red is following a set point. That is the basic of any PID. So in the last 2 videos we emulated the PID using a TC lab package, which is usually written in Python, and created a PID dataset. And after that, in the second video, we created an H5 model also. As you can see on the screen, a general temperature control system using PID looks like that. And there is a set point which we call TSP. There is a process variable called T1, and the error between these is a ERR, which is the difference between TSP and T1. That goes into the PID system. This is going to be an emulated PID or a programmed PID, and which produces a the power, the output called Q1. And this is a normal system, and if the PID is going to be in hardware, then it is a hardware based PID system, but if the PID is going to be in software, then it is software based PID. Now the objective of this part of the video is to create a Python program and test the performance of a PID H5 model. H5 model is an output of a created model which is stored in a file called H5 file, and this file will be used to predict the output of a machine learning based proportional integral derivative PID controller of a given system. The program will utilize a pre-trained LSTM model created as a standalone model in H5 format. That is what was discussed in the earlier video. Now, what are H5 and HDF5 files, etc.? So H5 stands for the hierarchical data format version 5, and it's a file format that is designed to store large amounts of data, and it also stores model architecture, parameter weights, and other information about machine learned models. And the Keras supports model save and load in HDF5 format. And you should note that H5 and HD5 are similar. They are just 2 different ways of how and when the model shall be saved. Now the program is going to utilize in this video a pre-trained LSTM model and a PID dataset containing the input features. The input features are nothing but temperature set point and the error, and along with the corresponding output Q1. The performance of assessment includes the visualizing and comparing the responses of the PID controller and the LSTM model. So now we have a PID controller which can be created through a program, and also you can create through using neural network, that is LSTM, and we are going to compare this LSTM model we have created, and we are going to compare with a PID controller. So in order to do this, the theory is that program employs a LSTM neural network to predict the output of a PID controller based on historical input features, the temperature set point and error, etc. It utilizes feature selection techniques, data scaling, reshaping to prepare the input data for the LSTM model. The LSTM model is loaded from a pre-trained file, and its predictions are compared with the actual PID controller responses. Now, the program steps, that is what you have to know. Actually, this is, a method of testing an LSTM, the neural network based model, which we have already created. We want to see how good it behaves. So first thing is you have to load the model, which is in the H5 format. That is like new model. You can simply load the model. And also you have a dataset sitting. You have the dataset sitting in a CSV file also. Both you have imported into a data frame. And this is how the data look like when you print. There are 5,400 rows of data with columns Q1, T1, TSP, error, etc. And the second part is select the relevant features using select K-bus feature selection method. This is an automatic selection of the feature method. How do you do that? These are the lines for that, and we are going to explain what it does actually. So now, what is select K-bus? It is a feature selection method in scikit-learn library that selects the top K features with the highest scores according to a specified scoring function. And also there is a score function. The F regression scoring function is used here. It computes the F statistic for univariate linear regression between each feature and the target variable, and it provides a measure of the strength of the relationship at K is equal to all. Like here you can see the K is equal to all you have specified. What it means? Meaning that the algorithm selects all variable features based on their scores. The remaining part you can simply stop the video and read it. And the third part is scale the input and output using min-max scaler. That is what is to be done. So that is this like S underscore X is equal to min-max scaler. What does it mean? It's responsible for normalizing the values of the features and the target variable to a specific range. So it's like creating a min-max scaler. Object is like S underscore X is equal to min-max scaler. This line creates an instance of the min-max scaler class, which will be used to scale the input features X. The same thing as underscore Y is another instance of min-max scaler and is created scaling the target variable Y. So what is the meaning of transform now? Now the fit transform method is applied to scale the input feature X. The same way for Y, the target variable Y is scaled using the fit transform method in the second min-max scaler object and S underscore Y using the lines given above. Now the fourth process is to prepare the data for LSTM training by creating sequences of input output. This is the univariate data. You can see in the green window. If the data looks like that, for example, and you want to window it actually for 3, a size of window size is 3, that means you split the data in such a way that you divide into many rows and columns, and row will consist of 10, 20, 30, then 40 is the output, then 20, 30, 40, then 50 is the output. Three data are grouped, and next one is considered as an output. So create a table like this, that is called sequencing. Here in our case it is going to be window is going to be 15. To sequencing there is a routine. You can ultimately what it does is it creates a table like this. Now all these details you can stop the video and read it clearly. That is looping through the data to create sequences and creating the input sequences and creating the output sequences, etc. Now the last part, the most important part of the video, that is like the splitting the data into training and testing. The testing data is what is important to us later. That is 20% of the data. 80% is used for the training. So the testing part, actually you can see that size is equal to 0.2 means it's 20%. So there is a train test split function. In this case 20% of data is reserved for testing and the remaining 80% used for training. So output variables will be xtrain, xtest, xtrain, ytrain, xtest, ystest. All these things will be there. And the sixth step is to use the pre-trained LSTM model to predict the PID controller responses on the test dataset. This 20% of test dataset is now given and passed through model which you have created right now, and it will predict on the X test and try to see how good a model it is. You can see that in order to do this there is some unscaling process involved, which is like inverse scaling for input features, and inverse scaling for the target variable also has to be done. You can stop the video and read this properly. Xtest underscore US contains the unscaled input features, whereas ytest underscore US contains the unscaled actual PID controller responses, and the YP contains the unscaled predicted responses from the LSTM model. Now the seventh step is to plot the set point, PID controller responses and the LSTM model response over time and save the plot for further analysis in a PNG file. So now, as you can see on the screen, the original PID dataset was looking like that with the 5400 rows, the Q1, T1, TSP and error as the columns. And finally, after the model prediction, the output would look like that for the test data. You can see that actually which set point is in black, actually it is here, and set point, whatever set point, it is varying set point, and this red curve, that is what it is trying to follow and settle at the exact value. That's the temperature T1, and the power which is going into the system is also varying with respect to time. It will take its own trend. So you can see QPID percentage and QLSTM percentage both are nearly matching. That means the LSTM model, that is a neural network model, is almost similar to the the PID, simulated PID. So this proves that the LSTM networks can be used for creating PID models successfully. So some of the advantages you can see in the screen, and the conclusion is going to be, we have demonstrated application of LSTM neural network for predicting PID control responses. You have compared the LSTM model with actual PID control responses, and you can do more reading in this reference. The TC lab actually has been taken from this particular reference, and you can look for more videos in the future. Thank you.